why do we need statistics in quality? Your business or your research concerns a product or service, and there are different variables that you consider important. Maybe this is waiting time for your patients, or execution time of your computer program, or the deposited film thickness or the current density in your integrated circuit, or the strength of your bicycle helmet strap stitching. All of these are variables from populations. Populations of waiting times, of execution times, of film thicknesses, or current densities. And all of these populations can be modeled. The science of statistics provides us with the means for describing populations with variability and methods for estimating population quality from samples. In quality engineering and management, we are interested in improving the process or product. We are interested in understanding the key inputs, our variables, and finding ways to change them so that the output is improved and controlled. And statistics are our key to this process improvement cycle. The following models are very often used in quality engineering, and most of them we'll see in this course. For example, control charts. These are used in controlling processes so that they produce products of uniform quality. They can also be applied, or they have been applied now, in service industries as well. Sampling plans are used for determining acceptability of lots based on samples taken from them. Designed experiments are used for determining the best combination of process parameter levels to obtain desired levels of the quality characteristics. We use regression and correlation analysis to determine which variables cause an effect and to what extent the quality characteristics are then affected. Reliability engineering is used in understanding the factors that affect the life of parts and assemblies in order to increase their life. And finally, tolerancing is used for determining the allowable variability in product or process variables so that the products can be produced economically while meeting customer needs. Now, we will be talking about some different numerical methods used for describing populations. And here I have a few terms which we should be familiar with. We have the term population. This refers to the collection of all items that are of interest in a given situation. The term sample refers to a subset chosen from this population. And whenever we use the term sample, what we really mean is a random sample. This is a sample taken in such a manner such that each item in the population has an equal chance of being included in the sample. Now, a few more terms. When samples are inspected from a population, you generate observations, and the collection of these observations we call data. And because the data come from samples, we will call that then sample data. Data are classified into two main categories. We have measurement data and attribute data. The measurement data comes from measurements of characteristics such as the length, the width, the weight, the diameter, the amount of impurity, and so on. These are in units such as inches, pounds, kilograms, cubic centimeters, and these are known as quantitative data. Metric data, data that can be quantified. Attribute data, on the other hand, comes from inspections in which the units are classified based on attributes. Examples could be finish, color, taste, smell, fit. And the results from attribute inspection will be in things like counts, such as the number too rough, the number too dark, the number too tight, and so on. So attribute data is qualitative data, and this can be either nominal, meaning that the data is differentiated by categories or classifications only. There's no order to these categories. This could be hair, color, nationality, religion, for example. And ordinal, meaning that there is a natural order or ranking in the categories, although there's no quantitative difference between the categories. An example here would be the number of stars for a hotel ranking or classifications such as poor, average, good, or excellent. We know that excellent is better than good, but we don't know by how much. So with the attribute data, we said though, we were looking at the qualitative aspects. Is it, how rough is it, how dark is it? And then once we reach a certain level, we will consider it then defective, too dark, too rough, too tight, and so on. Many of you are already familiar with the concept of the average value of a population. This average value, or mean, which is given by the Greek letter mu, represents the center point around which the data, the population, is distributed. The standard deviation, or sigma, of the population represents the amount of variability, or the dispersion in the data about the center point, about the mean. So you can see that here in this example picture. The square of the standard deviation is called the variance. So please memorize those three terms because we use them now for the rest of this course. And we'll look at them in more detail then in the next section, how we calculate these. Now, if we take a sample of our entire population, we can calculate the average, the mean, and the average and the standard deviation. We can estimate them from the sample data. And this is then an example of our using statistics to estimate the population model from the sample. The sample average is given by the symbol X bar, and this is the sum of all the I observations in the sample of I elements divided by N, where N here is the sample size. The sample standard deviation, or S, is the square root of the sum of the square difference of all the observations in the sample divided by N minus 1. And again, these two give us a measure for the variability and the center point of our sample data. Now let's go to summarize everything. If we have a population where mu and sigma are the population mean and standard deviation respectively, we can take a sample from the population and we can calculate the sample mean X bar and the sample standard deviation S from our sample. X bar and S are our sample statistics, and mu and sigma are our population parameters. A last note at the difference between quality and variability. Now here I have two bullseyes and two sharpshooters. Who is the better marksman? Is it marksman A or is it marksman B? What would you say? The bullseye here on the left, or on A I should say, it shows that we have always shots that are just off the target. While B, marksman B, he's consistently shooting around the target. Which is better? Now what we have to learn from this, and this is an animated slide, so watch marksman A. To reduce the defects, we need to reduce variability and target the mean. And in this case, it's typically easier to change the mean than it is to change the variation. Because every population has some degree of variability in it. Whether it's the diameter of your bolts or the hardness of your piston rings or the amount of cereal in a box, all the populations have some variability. And it's this variability, the difference from unit to unit, that is the cause of poor quality. And therefore, this variability needs to be measured and managed in the effort to achieve quality in products or services. And in this case, we see that if the sharpshooter A would just move a little bit over, he would be shooting consistently on target. For B, on the other hand, we would have to reduce the variability, which is generally a little more difficult. Okay, so every population has variability in it, and excessive variability causes the poor quality. And here we have an example of the fill weights. So I could write this in here. The fill weights of 20-pound boxes. And you can see, it should be 20 pounds, but we have a variation in the fill weights of our different boxes. And we have here a lower specification. We have some points that are either at the lower specification or lower. And this means that the boxes are not acceptable to the customer. So the problems in this line A here have to be resolved. So what you could do is you could just fill all the boxes more. That would mean all of these weights would go up. But it also means you would have the high points also going up. And this means the boxes that are already full or overfull maybe would not be able to be closed. And this also means that you would maybe be putting more product in than is actually necessary. But if, on the other hand, if this variability can be reduced, as we see here in the production line B, then we can have a consistent filling of our boxes that is above this lower specification limit and doesn't cause boxes that are too full. So there's savings for the manufacturer. The customer will not receive any box with a fill weight that is less than the specification. And in this particular case, they actually had this problem, and there was a problem with one of the filling chutes. There was a little bit of a leaky shutter, and once that was repaired, they were able to control the variability. This is a simple example from industry to show how excessive variability causes poor quality and waste, while smaller variability avoids waste, results in good quality, and in this case also results in saving money by not filling the boxes too much.